Welcome to the session's talk, Enabling High Assurance Sensitive Container Workloads with Encrypted Images. My name is Andrew Xu. I'm an engineering manager at Docker, and I'll be your MC for the session. We have here joining us Brandon Lum from IBM. He's a researcher at IBM that designs, architects, and develops for problems at the intersection of cloud and security. He works on various security areas such as container, content protection via encryption and image signing, container trusted identity, and identity-based data fencing. Techniques to reduce the attack surface on the kernel and a container, and container cluster update planning. He'll be covering for Justin Cormack. He won't be able to join us today. And fun fact about Brandon, he used to play guitar in an 80s rock band. So when he's up on stage, you can let your imagination go wild. He'll be talking today about details of the encrypted container images and demonstrate Docker images which can protect sensitive data and code or algorithms embedded in your pipeline from build to runtime. He'll also show how technology can provide additional enterprise security capabilities, such as enforcing policies on sensitive content protection and geofencing execution. Please give a warm welcome to Brandon.
All right, great. Thank you, everyone, for coming. Thanks, Andrew, for the kind introduction. Today I'll be talking about enabling sensitive container workloads, and really what this is going to be about is encrypted images. Okay. So just to give you a bit of background, so my name is Brandon. I'm from IBM Research, and this work stemmed out from IBM Research really to do container encryption. And we've been working closely with Docker, so that's why Justin's involved. We've been talking a lot with the container maintainers, and a big thing is we want this to be part of the entire ecosystem. All right. So unfortunately, Justin can't make it today. He's tied up with a few things. He's a busy guy, so let's get started. So the first thing we're going to talk about is threat models, because we're talking about security. And because we're talking about images, naturally, the first thing that we're addressing is the scenario of threats to the registry, right? So, for example, if your registry gets compromised, if your registry gets hacked, what happens, right? And the idea is that if you've been keeping up with security functions and features within registry and image like DTR, you know that there's something called the notary service, right? And the notary service really helps provide with image signing and verification. It is able to say that whatever you're running in your cluster is valid and it's not compromised code, right? So even if an attacker hacks a registry and changes the data within the registry, you will still have the assurance that all the containers running in your cluster will have the correct integrity. However, what this doesn't protect against is when you have actual sensitive code. So this can be things like trade secrets, secret trading algorithms, things that you can't protect. And if they get access to the registry, they can download all the information and all the code which is sensitive, right? So this really is one of the ideas that we want to show here. So example of this, this was from Justin. So Coca-Cola, for example, has a secret recipe, and the secret recipe is put in a gigantic physical vault, right? So as with Coca-Cola or Pepsi, you have something that's a trade secret that can't really be patented or copyrighted. So what we are trying to do with encrypted images is we want to make this part of the ecosystem. Basically, the idea is during the build process, we do additional steps. So you build your image as per normal, you want to perform additional encryption on top of it before you push it to the registry. And at the runtime, you have to decrypt the image before you run it, right? So what this means is in between the build and the run phases, your image is always encrypted, whether it's in the registry, whether it's in transit, whether it's been leaked somewhere. It will not be able to be decrypted by any unauthorized personnel. So what does this mean? So obviously, first thing is if I compromise the registry, I can't get the code that's in the registry. What this also provides is this assurance that whatever code, my image is encrypted all the way from the DevOps pipeline to the runtime in my cluster. So a little more subtle feature that comes with this is something that we call execution boundary control. And so what this is it's trying to make this assertion that if my code is running, I know that it's running in my cluster or a set of approved hosts, right? So how this works is you encrypt images and you have some kind of key management and key distribution to show that only certain machines or certain clusters will have the decryption key, and therefore only encrypted containers can run on them. So in this case, a policy that one can make is say image X can only be run on EU nodes or depending on how you set your security boundaries. So a big question is, do we have to sign our images still, right? We have encryption, you can't read it, what does this mean? The answer is yes, you still have to sign images because encryption really focuses on the confidentiality of the images and the content of the images, but it doesn't really address this idea whether, am I running the image has been scanned and so on, right? So old images can be encrypted, but they can still be vulnerable, right? So we still need image signing and image provenance controls and admissions to be able to ensure that we are running the correct things. All right, so how does this work underneath? Let's get into some details. But before that, let's go through a really quick encryption primer. So we kind of know what the tools we are to build this is, right? So unfortunately, it won't take long like the image seems to suggest. So let's just get started. Right. So two types of encryption that are important here. We have symmetric encryption and asymmetric encryption. I'm going to go really quick. So the idea in symmetric encryption is really simple. We have a message that we feel is sensitive. For example, this is my secret message in gray. And to encrypt it, we generate a key, which is the yellow key, and we use that key to encrypt the secret text. And what we end up with is the ciphertext in the red box. And in order to decrypt this, I send it to someone, and they can use the key that was initially generated to decrypt the ciphertext, right? So this is really simple, and the good thing about this is symmetric encryption is really fast. And the good thing about that is that because it's fast, it's really good for big amounts of data, it's like images. The unfortunate disadvantage here is that, as you can see, that the key that's used for encryption and decryption has to be the same key. So there's some challenges in being able to share this key because it's key to the it's secret. So we need some way to be able to communicate the key to the recipient securely. Right, and this is where asymmetric encryption comes in. So asymmetric encryption is pretty much the same setup here, except that we have two keys. So in asymmetric encryption, we have a key pair that consists of the public key and the private key. And the idea, as the name suggests, is that it's asymmetric. So the key that you're using for the encryption and the key that you're using for the decryption is different. Right? And the great thing about asymmetric encryption here is that the public key is not secret. I can distribute the public key to anyone that I want. So for example, if I wanted Justin to send me an encrypted message, what I would do is I would generate my key pair. I'll keep the private key to myself and pass Justin the public key. And basically, Justin will use the public key to encrypt the text, and I'll use my private key to decrypt the text. So this solves the weird key sharing problem that we saw earlier in symmetric encryption. However, it is a very slow encryption process, and it's not great for big data. All right, so with that out of the way, let's talk about what the actual encryption is going to be doing, right? And before we go into exactly what the changes within the container specifications in the OCI images, let's take a look at the general flow. So someone like you and I, as developers, what would it look like when we use this technology? Okay. So with any crypto scenario that we have our two favorite people, Bob and Edith, right? In this case, Bob wants to send a message to Alice, and so Bob has a Docker image ready over here, right? So to some of you, what you're about to see in this flow will look very, very familiar. And this is because basically what you're seeing is very standard in terms of how encrypted messages are being passed, right? So if you're familiar with something like email encryption, OpenPGP protocols, this will look something like that. Right. So we start first because the image is big. We want to use symmetric encryption. So what our system does is it generates a symmetric key. And we then use the key to encrypt the image. So what we get now is an encrypted image. But Alice will still need the key in order to decrypt this image. So what we do is we use a public key, Alice's public key. And then what we do is we do something called key wrapping. So the idea is we are trying to create this envelope that is sealed with the key in it. And this basically says that this envelope only can be unwrapped or unsealed by Alice. So with this, what happened is now Bob can expose this image, make it available to Alice, and the rest of the world by doing a Docker push. So he does a Docker push, it goes into the image registry, and now everyone can download the image. But the great thing is that only Alice can decrypt the image. So what happens next on the decryption side is pretty much the opposite of what we saw Bob did, right? So we have the wrap key, and in order for Alice to obtain the symmetric key, she uses a private key to do the unwrapping to obtain the decryption key. And she then uses the decryption key to perform the decryption on the encrypted image to get the resultant Docker image that she can then run. All right, great. So now that we've seen how a developer like you and I can use encrypted image and how we can send encrypted images to each other, what do the images actually look like? So because one of our goals is really to make this part of the ecosystem, we want everything to be in the standards. And so what we are proposing is based off the OCI image spec. So what you see here is an example of the OCI image spec. What you see on the right is a JSON object, which is an image manifest. So there are a couple of things to the image manifest. So basically, it's a JSON object. You have a bunch of metadata at the top. And the things that we are really looking at here is the content of the images. So image is a file system, and the file system is represented by layers. And what these layers are actually, what they end up to be is just a collection of files, right? So in the OCI image spec, a layer is a collection of files that is tar and gzip together. And that gzip tarbomb has a hash representation, and that represents the layer itself. So our proposal with encrypted container images is two simple changes, right? So the first simple change is we're adding a new media type called the encrypted media type. So in the usual case, we have something like tar gzip media types. Now we're saying tar gzip plus ENC for encryption. So a media type with an encryption suffix. And what this basically says is that if a runtime or an image builder is to look at this, they basically know that on top of anything that's been done, which is, for example, making the tuple, we've added an additional step to perform encryption. And so the handler, for example, container D, which we targeted for implementation, would need to know how to decrypt this image or this layer. Right. So really what we're doing is additional encryption step, which we perform a block encryption, and the resultant binary block will be the new hash of the layer. So the second change we see over here is we've added this annotation called keys. And I know this looks a bit odd, but there are reasons for this that I'll go through in the next slide. The idea is that the keys annotation contains all the wrap keys that we talked about. So in our previous example, when we had the wrap keys for Alice, this wrap key appears here in the annotations. So if I wanted to encrypt the image for multiple people, I would have multiple entries within this annotation with all the wrap keys for the recipients. All right, so why did we design it this way? Why did we choose to encrypt layers instead of encrypting the whole image? So the decision to encrypt layers is that it allows us to benefit a lot about what people love about container images. People love layers, people love deduplication, and we want to benefit from that, right? In VMs, it was a little bit difficult because the entire thing you had was an entire huge block, and you couldn't really decompose it very well. So what doing encryption on the layers means is that in the usual case, you have an image, and your image has multiple layers. You have the operating system like Ubuntu 16.04, and then you have some kind of middleware, and finally on top are your secret algorithms or sensitive code, right? Now, the sensitive code or secret material generally is pretty small, but you don't want to re-encrypt everything underneath, right? Ubuntu or the middleware that you're running, like Nginx, isn't something that's secret. We don't have to encrypt it. So what doing encryption at the layers allows us to do is to benefit from deduplication. You know, these huge chunks of huge layers can still be deduplicated with non-encrypted images. So the second design decision about putting the keys in annotations, the reason that we did that was that we could encrypt the layer once. So we had the layer is a huge blob, we can encrypt it once, and then we can have wrap keys in the annotations for multiple recipients, right? So for me, for Justin, for Alice, and in the case that I wanted to add a new recipient, right? If I had everything in the blob, what happened if I add the wrap key within the blob is that the blob would change. And when the blob changes, it means that the registry no longer can deduplicate it. Right? So in this case, I'm still able to add more recipients to the image without actually having to re-upload the entire image. All right, so let me go ahead and do a demo. So this demo that I'm going to show, all the implementation that we've done is in containerd, and so that's what you will see. Okay. All right, let me make this a little bit bigger. Can we see this? Bigger? Okay. How about now? Good? All right, awesome. Okay, so what we're gonna do is we're gonna build the image and we're gonna encrypt it. So we're just gonna list what we have here. We have a Docker file, and this Docker file is really simple. It says, I have my Ubuntu-based image, and I'm gonna copy this secret.html in it, and my entry point is bash. And we can see secret.html here is just something says that this is a secret page. Right. So what we're going to do is we're going to do a Docker build as per usual, everything that we're used to. And the next thing we're going to do is, because all our implementation is in containerd, we want to export this into containerd so we can work on it. So what this command is doing is basically exporting the image from Docker and then importing it into containerd. So CTR, for those that are not familiar, is a client tool that interacts with containerd. So you can basically invoke almost all of the containerd APIs. Right. So what we've done in our work here is we've added within the containerd image command, we've added several capabilities. So we have the encrypt feature, we have the decrypt feature, as well as a layer info feature, which we'll take a look at. So let's first list the image. We can see we have our imported image over here, secret container latest. And what we want to do is to encrypt the image. Okay, so this command says encrypt image, my secret image latest, and what I want to do is I want to encrypt it with a new image tag with enc as the image tag. And the additional parameters I'm passing in here is I want this image to be encrypted for Alice. So I'm passing in Alice's public key. And this last argument over here that says layer -1 is saying that I want to only encrypt my topmost layer. Because as we saw in the Docker file, the only secret information we have is copying secret.html at the last layer. So doing this, we now have the new image, and we can take a look at this by doing invoking the command that we added called layer info. And so what we see here is the layers of the image. And on the bottom here, which is the topmost layer, we can see that this layer was encrypted, and the encryption scheme we used for the key wrapping was JWE, which is JSON Web Encryption. And here is one recipient that we have. So for key wrapping, we support multiple protocols. So we support JWE, we also support PKCS7, you can import certificates. We also support PGP, so you can send encrypted images to your friends that use GPG. Okay. So the next thing we're going to do is we can push the image. So what this says is I'm going to push this to my local registry with the latest tag, and this is the encrypted image. Right. So just a note here, the only reason we're using the local registry is because we don't need changes to the registry. It's just that the one that Docker Hub is using is not the latest. And the latest built in the registry repository supports OCI images. Right. So what we just saw is kind of what Bob would do. Now let's take the persona of Alice, and we want to pull and decrypt the image. So what we're going to do here is we're going to pull the image from the registry. All right, and so I'm going to list the images. So we have the image that we downloaded from the registry. And what I'm going to do now is I'm going to try and decrypt it. So I'm going to say sudo ctr image decrypt and the image name. Right. And obviously I can't decrypt it because I haven't told containerd where to find my private key. So if I was anyone except Alice, I would see this message basically saying that missing private key needed for decryption. So we can fix this because we're Alice by providing the key. So Alice private key. And now if we look at the image, we can see that it's no longer encrypted. We don't have the message over here saying that they're recipients of this encryption. So finally, the thing that we can do is we can try and run this image. So sudo ctr run localhost, and this should work. Oops. The container already exists, so I'm gonna delete that container. All right. So now I'm in the container, it's bash, it's not interactive. So I'm gonna just cat the page. And we can see that this is the decrypted file that we initially had in the image. So before I go back to the slides, I want to show an example that you can use with PGP. So if I can get this right. Okay. So now I'm going to perform the encryption again, just to show what an example would look like. So if I wanted to, on top of being able to encrypt this for others, I want to also encrypt this for myself. So what I can do is over here we have my GPG keyring. And so we have one for Michael Ruttl. We also have one for myself. And so what we're going to do here is we're going to encrypt it with additional field that says recipient to myself. So we configure the client in a way that it already passes and realizes that if it's an email, it goes to GPG keyring. Oops, it already exists. So I'm gonna encrypt this. All right. So now if we look at the layer info, we can see that on top of the encryption, let me make it a little bit smaller. So on top of the encryption key we had for the JSON web encryption block for the wrap key, we also had this recipient for the PGP wrap key. All right, so whatever you just saw can be available in the branch of this pull request that we have open right now. So you can go in, clone the branch. There are several steps within this documentation that we have over here that you can reproduce whatever you saw in the demo. We also have a unstable latest experimental feature branch that we are working on integrating with other orchestration systems if you want to play with that as well. So some additional information for ecosystem developers. We have an exposed API for encrypting, decrypting the image, checking authorization for the image. This is especially useful when you are a runtime that wants to check without having to actually decrypt the entire image again. So a bunch of APIs available for developers. Which brings us to a small caveat that we kind of have not addressed yet, which is because now that we are encrypting images, the image content is protected within the registry. And this doesn't really go well with some kind of scanning services. So some scanning services depend on the ability to pull something from the registry, to introspect the packages, the content of the image, and then come up with a vulnerability assessment, right? This isn't a big issue. This is something that we just need to know how to deal with. So basically, if scanning services can also integrate decryption, in the build pipeline, we would say that we are going to build this image, and when we are encrypting the image, if I trust the specific service to do the vulnerability scanning, I can create a wrap key for them like I did for Alice. There are other methods of this. If you're interested and want to talk about this further, I'll be happy to chat about this. There are multiple options of getting around this. All right, so finally, some of the future work that we're looking at. The first thing, of course, is to hope that this becomes an integral part of the container ecosystem. So we have an open issue that's part of the OCI image spec. We have a PR that's now open. So if you really like this and would like to see it in the image spec, please chime in on the matter, give us your feedback, give us your support. That would really help a lot. All right, so the second thing is what we didn't see in this demo, which is integration with orchestration systems, right? So this is something that we have to follow up better on. We have some working demos with Kubernetes at least. We have a KEP that's open that we are trying to create something called image decrypt secrets, which are kind of the parallel to image pull secrets for decryption. And of course, when the Docker CLI will also get all these features once Moby and BuildKit integrate with Containerd. Finally, the one thing that we are looking at as well is to make the encryption a bit stronger. So this is to leverage hardware encryption, which seems to be all the rage, HSMs, TPMs, and all that fancy stuff. So the idea is we want to be able to interface with these key management services, use the key wrapping and key unwrapping services that they provide. Another big thing that we're looking forward to is to have FIPS compliance for enterprise solutions. Certain enterprises may have their own libraries or their own encryption libraries for their FIPS compliant that they've gone through the process. And we want to allow these enterprises to be able to obtain that FIPS compliance through their own libraries. All right, so that's all that I have for today. I hope that this was interesting. And here are the links that you may find useful. Thank you.
Thanks very much for that, Brandon. I think we have a few minutes. We can take some questions. If anybody has any questions. Yes?
Thank you. On your suggestion for the OCI extension, have you considered using something like HashiCorp Vault or CredHub to be able to save those keys in a secure manner and distribute them that way?
Yes, so we actually have a working solution where, so there are multiple ways to distribute the keys. The two things that we've looked at are, there are two models that we boil down to. One is, do I trust Kubernetes secrets or Docker secrets, or do I have my own key management solution that I have that manages all my keys? And so we have a proof of concept for both models, right? We have something where we use an orchestration system like Kubernetes or Docker Swarm to store the secret keys. We also have a solution, a proof of concept that we have, which is part of the experimental branch, where we basically have a daemon that calls out from containerd into something like Vault, right? So we have Vault support that does this. We also have KMIP support. So if you have any key management server that talks KMIP, we can get keys from that. Yeah.
Hi, yes. I was wanting to ask, how do you specify the algorithm that you use for encryption?
That's a good question. So so the wrap key that we specify is a little more than just a wrap key. Which you did too, right? You need to know what are the specifications, what's the nonce used in the blocks and stuff like that. So the wrap key that you saw was actually a JSON object containing the symmetric key, the cipher that is used according to the INA registry, so like AES, GCM, or AEAD, as well as all the options according to IRC standards, so like the nonce that's required to initialize the IV and stuff like that. So all that's all going to be in the wrap key.
Okay, is that going to be specified in the spec? Or?
Yes, that's going to be specified.
All right, and is it going to be, I guess my concern is that it's going to be future-proofed such that we don't need a new specification to introduce new algorithms. Because that's hurt us very bad in some RFCs in the past.
Yeah, so that's something that's, so there were two approaches that we could do. One was like you take the encryption message protocol like JWE, and then we decompose it. Well, one of the requirements was we wanted to split the wrapping of the keys with the actual block of the data for deduplication. So what we ended up, the design decision we ended up with was to specify that as a JSON blob, like you said, right? So we have a set in the PR that we've opened for the OCI spec. What we've done is we've just said, okay, here's the specification, here's the IANA registry. You technically should be able to use any encryption scheme there. Yeah, but if you have more ideas or a better way to scope down things, we'll gladly do so. I don't know whether we want to support all encryption protocols because some of them are not great. Yeah, thanks.
So it seems like any way you cut it, the secret zero is still a problem, right? You still got a way to deal with the, I guess, what's your recommendation of dealing with secret zero to not have a single point of failure that you've got your encryption, you've got this, you've got that.
Right. So the approach that at least we are looking at internally, this is a huge problem because really it's about trust bootstrapping. How do I bootstrap my trust to a node, right? If I understand that correctly. The approach that we're doing with is we want to use the root of trust from a TPM from a machine, right? So all the way from the data center, when we provision the machine, we do measured boot. We have something that so we measure the kernel all the way up to the orchestration level. We have something called integrity measurement architecture, which is a kernel module that basically measures every binary that runs on the machine. And what we are doing is, for us, we believe that that level of trust, as well as the security of our provisioning process, will be a attestation to whether that node is able to obtain the encryption key from Vault or whatever key management service. But we also want to take this a step further where the key should not even be on the host, which is you perform the unwrapping. That helps a little bit, but doesn't really solve the problem because you still need to authenticate the session, right? That way, the only thing that you get from that is you prevent offline decryption. So whenever there's a compromise or someone's using your image, you know that they actually performed the decryption by talking to your key server. Yeah, I hope that answers the question.
It's a great question, guys. It's like really insightful stuff. All right, one more over here.
Hi, thank you very much. This is a very interesting talk. So one of the things that I think people learned from the recent redacted incident was that having a secure underpinning is really important to what you're doing. And having, you know, a more general secure framework that's been really well thought out, it helps. So have you looked at integrating this into things like in Toto that provide a secure left side framework for security? Because I think it would actually fit very well in there.
Right. That's a good question, and it's funny because I was just talking about in Toto and to my group. So the answer is yes. So before I worked on encryption, one of the things I worked on was actually the image signing part of it. So I'm a firm believer of image provenance, supply chain security. So in Toto is great because it allows us to make more fine-grained guarantees and in a decentralized way, right? The thing that and it's also a big issue that we have also because one of the problems that we're running into is we want to enforce a DevOps pipeline. If we own the entire DevOps pipeline, we can make better guarantees, but a lot of the time customer requirements are, you know, they want to use their own DevOps solutions. And so something like Intoto is something that we're looking at. We're looking at Tecton as well as a DevOps orchestrator, and hopefully, because Tecton also runs on Kubernetes, we can add a lot of our security that we have on top of Kubernetes already. So yes, the short answer is yes. Thank you.
Any other questions? Okay, if not, ask you to thank Brandon again for his talk. Okay.